Hey, let's learn about scalars and vectors. This is an important one, so please make sure you're taking notes and making some sense out of this. All right, so when we take measurements, oops, I think I hit the thing too many times. We sometimes have what are called scalar quantities that we measure, and sometimes we have things called vector quantities, and we need to right away distinguish the difference between the two. So a scalar quantity is a measurement that has no direction associated with it. So scalar quantities have an amount, which we call the magnitude. Where's my mouse? Okay, which we call the magnitude, but they're not associated with any particular direction. So examples that we typically deal with are time, uh, the distance that an object has traveled, how fast an object is going, and the mass of an object. I mean, how many kilograms of matter it contains. Now, some of these have vector similar values measured in vectors, but we'll get to that in just a second. So let's just talk about what a vector is. So a vector, I'm waiting for my screen to change here. Okay, a vector is a measurement that does have a directionality to it. So they are directionally dependent. So a vector quantity has both an amount, which we call the magnitude, but it also has a direction associated with it. All right, and that direction very much matters when we're dealing with vectors. So examples of vector quantities where there's both a magnitude and a direction would be things like displacement, how much an object has changed its position, velocity, the speed and direction which an object is traveling, the acceleration, force, momentum. Oh my gosh, these four things here are the majority of what we talk about in AP Physics 1. You're going to get really good at velocity, acceleration, force, and momentum, and these are all vector quantities that you'll do well with as long as you learn about vectors right out of the starting block, like we're going to do today. So the thing about working with vectors is you have to keep track of the direction. The direction matters, so you can't just ignore it. And the easiest way to do this is to assign the values being as either positive or negative. That's the best way to give a directional distinction when dealing with a vector quantity. So we tend to talk about positive and negative directions. So when we're dealing with vectors, that positive or negative, it has to do with the direction of the vector. Now, unless we have reasons to do otherwise, and sometimes we will, the standard convention is to say, hey, look, let's do this. Anytime something's moving to the right or the east, we're going to call that the positive direction, just like we would, if we were just doing a graph in math. And if it goes to the left or the west, we'll call that the negative direction. Similarly, if something's going up or north, up my page, I'm going to call it the positive direction. And if it's going down or south, we'll call it the negative direction. And if we just stick with that, we can't go wrong. Now, there'll be times when we can make our problems a little bit easier by choosing the other direction to be positive. But for right now, let's just go with this. Now, distance is a scalar quantity. That means the direction is irrelevant, is not part of it. We don't care about the distance. So it's just how far an object has traveled. So here's a classic example of a distance. A person walks 2 meters to the right, changes their mind, they walk 6 meters to the left. How far did that person walk? Well, you don't have to be a rocket scientist. I think you asked any kindergarten, well, that person walked 8 meters, right? They walked 2 meters this way, they walked 6 meters that way. That person just walked 8 meters. Doesn't matter which direction they walked 8 meters. But displacement is a similar measurement, but it's a vector measurement. So displacement is how much has the position of the object changed. Now, that's a little bit different. We designate this with delta x. Now, delta is a symbol we use quite a bit in physics. It just means change in. It means final minus initial. And so the change in the position of an object, the delta x, or displacement of the object, well, let's look at that. That's a vector quantity. So in this case, a person walks 2 meters to the right, they walk 6 meters to the left. But this time, I'm taking into account the directions. It's a vector measurement I'm looking for, displacement. So in this case, I'm going to say, look, 2 meters to the right, that's the positive direction, positive 2 meters. Plus, they also walk 6 meters, but in the negative direction. So I'm going to designate that by saying -6. Now, when I add 2 and -6, what do I get? I get -4. Well, negative means the person was displaced a magnitude of 4 meters in the negative direction, which in this case would be to the left or to the west, whichever I choose to say. So it's quite a different thing. Yes, the person walked a distance of 8 meters, but they displaced 4 meters in the negative direction. Now, often when we're trying to figure out vectors, we find it easy to use, or useful, I should say, to use the tip to tail method. And basically, what we do in this case is we draw an arrow that represents the vector. And when I do this, The length of the arrow is going to represent the magnitude of the vector, and then the directionality will be given by making it into an arrow rather than just a line. So here I have 4 meters to the right. 2 meters to the right would be an arrow that's still pointing to the right, but it's only half as long. 3 meters to the left would be, a little bit longer. This one, a little bit shorter. This one, but it'd be pointing in the opposite direction. Now, if I want to add these 3 vectors up, a person walks 4 meters to the right, then they walk 2 meters to the right, then they walk 3 meters to the left. What's their displacement? Well, if I do that, I know, so I'm making a recording. Okay, sorry. Okay, yeah. I'm just going to keep going. So in this case, what we do then is we just add them to the tail. So I start with either one of the vectors. It doesn't matter which one. I'm going to start with the 4-meter vector. So I draw a 4-meter vector going to the right. Then at the tip of this one, I'm going to put the tail of the next one, of the 2 meters to the right one. And then at the tip of this one, I'm going to add the third one, the tail of the third one, that goes 3 meters to the left. And then the resultant vector, or the sum of the vectors, is going to be found by going from the starting point to the ending point. So I'm going to start here and I'm going to aim it that way. So I call this the resultant vector. So in this case, the black one is showing the resultant vector. I start at the beginning, I end at the ending. And so this distance here is 3 meters to the right. That means I've displaced 3 meters in the positive direction. I can also use this when I'm dealing with 2 dimensions or 3 dimensions, although in AP Physics, we're not going to have to deal with 3 dimensions. So what we do then is this. I say, all right, look at this. I want to know what the displacement is of an object that travels 4 meters to the east, 3 meters north, 3 meters west, 5 meters south, and 1 meter west. All right, whatever. Okay. So I start here. I go 4 meters in the positive direction. To the right, I go 3 meters in the positive y direction. Then I go 3 meters to the west, which is the negative x direction. Then I go 5 meters to the south, which is the negative y direction. And then I go 1 meter west, which is the negative x direction. And like I did before, I'm going to start where I started. I'm going to end where I ended. So this will be my resultant vector right here. And so the displacement is 2 meters in the negative y direction, south. What if this happened? Okay, the person walked 4 meters in the positive x direction, east, and then 3 meters in the positive y direction, north. What's that person's displacement? Well, in this case, I'd start here, I'd end here. And since this is a right angle, I can use Pythagorean Theorem to figure out that this resultant vector needs to be 5 meters long in magnitude. And because what I have is the square root of 4 squared plus 3 squared. Okay. And in this case, I'll just say to the northeast, we could use trigonometry, and later in the year we will, to figure out exactly what this angle is. Now, we often in physics find this to be the case. It's quite useful to take a vector that's going at an angle like this and resolve it into x and y components. In other words, think of this as if that's the hypotenuse, what are the two sides of the right triangle that lead to that hypotenuse? So in this case, I'd go this way and I'd go this way. So that would resolve into a 3 meter west vector and a 5 meter north vector. Okay, thanks for watching. That's vectors. We're going to use them a lot this year, and we'll start practicing them as soon as you get to class tomorrow.